another idea about the production of homochirality in the fundamental molecules of life. So we saw first the idea that we could have a pulsar which is photolysing some of the molecules and therefore only allowing some molecules to survive, which are particular chirality. We also saw that we could form molecules on chiral surfaces, or better said, surfaces which have greater affinity to some chirality over the other. And if life started, for example, on clay surfaces, then one could imagine that we could have such a clay surface which would attract only left-handed amino acids, for example. But it's very hard to imagine that we couldn't have both chiralities and both systems evolving simultaneously and getting equal number of right and left-handed fundamental molecules of life. We also saw that there's a small violation of parity in the weak force, and that gives rise to a slight difference in the energies, the Gibbs free energies of the two different chiralities, but only a very, very small value, and it doesn't seem it's sufficient, even looking for amplification effects to describe the homochirality of life. So the new theory we have is that, well, at the ocean surface is where circular polarization is greatest, and in the afternoon it's different from in the morning. So in the morning it could be left-handed, circularly polarized, and in the afternoon, right-handed, circularly polarized. And the closer we are to the ocean surface, the greater the component of circular polarization. So it gets up to about 5% maximum when you're very close, about 100 microns from the ocean surface. And we use that in this UVC denaturing of DNA process, this UV tar process, assisted not only by the UVC light, but also by the temperature in the afternoon, the ocean surface, which had increased. And so that gives us a little bit greater replication of right-handed DNA with respect to left-handed DNA. And so over time, we do the calculation, and that's where I stopped, or where the video ended, the last video. So this calculation is really based on this recursion relation, which is the number of left-handed DNA in a given generation I. And it's dependent on the number in the previous generation, I minus 1, okay, plus a component which depends on the probability of absorption of a left-handed circularly polarized light on left-handed DNA and right-handed circularly polarized light on left-handed DNA. So these are the probabilities for absorption with some kind of parameter, which is like the quantum efficiency for denaturing. And so we have two of these equations, one for left-handed DNA, one for right-handed DNA. And we have this small increase of about 5% in circular polarization in the afternoon, and let's say that's right-handed. It would depend on which hemisphere of the Earth you are at. It would be either right or left-handed in the afternoon. And that we have a small circular dichroism. That means that the molecules absorb slightly more right-handed circularly polarized light than left-handed, but only a small amount, less than 0.1%. Okay, 04 and 6,000. So if we set the probabilities for absorption of a right-handed photon on right-handed DNA equal to 1, then you can, just thinking about this, you can convince yourself that the probability, for example, of left-handed circular polarized light being absorbed on left-handed DNA is just this equation, and so on for the others. And then we develop what we call the chirality, which is just number of left-handed minus number of right-handed DNA over the sum of the two, the left-handed plus right-handed DNA. And this is a recursion relation, so it's a function of generation. And because each generation is 1 day in the Archean days, which were about 16 hours long, then we can calculate how long it would take to get to 100% chirality or homochirality. And it turns out, well, there are two different calculations here. One is assuming that the energy, the photon, is absorbed and given these probabilities, but it doesn't matter what the energy is absorbed, but these are probabilities. So these are continuous probabilities. The other calculation is assuming that there's an energy threshold. So for example, we need above a certain number of photons absorbed on a particular DNA in order for it to denature. Because what can happen, we can absorb a few photons and then the DNA denatures in a section of the DNA, but it goes back together again with time. So we need a certain number of photons. So it's a threshold, if you like, in energy to being absorbed. And in that case, well, we have three calculations here for the three different systems. These are double-strand DNA. This is a short strand. This is longer strand DNA. And this is DNA with tryptophan. Okay. Now we see that if we don't include the threshold, so just allow probabilities, just taking into account probabilities without taking into account that probably we need a threshold in order for DNA to denature, then we get these three curves for the different DNA. So for DNA with tryptophan, we could get homochirality in about 19,000 years, okay, which seems like a long time, but in terms of the time that life has been on Earth, it's an extremely short time. It's just a blink of an eye. And these are the results for the longer strand DNA without tryptophan, without the amino acid. It would take about 1.4 million years to get homochirality. That's still not very much time. But you can see that if we include a threshold for energy, that is only if the energy absorbed through the photons is sufficient to go over this threshold that we get complete denaturing, then those times decrease dramatically. So for example, for the case of DNA with tryptophan, it would take only 117 years, 137 years to arrive at complete homochirality. And this is for the case of DNA with tryptophan, and for the others, well, it would take maybe a few hundred or 1,000 years to get to homochirality. So even with these very small amounts of extra circular polarized light in the afternoon, 5%, and even this very small difference in the absorption of this circular polarized light for left or right-handed DNA, it still takes very little time, 137 years, for example, in this case that we have tryptophan together with DNA, in order to get 100% homochirality. Okay, so that's the homochirality of DNA or RNA. But what about that of amino acids? We know that it is opposite. So if DNA is right-handed, as it is in nature, then it's the left-handed amino acids which we find also in nature. So the question is why left-handed? Well, it turns out if you calculate the Gibbs free energies for right-handed DNA with left-handed amino acids, it's less than, for example, left-handed DNA with left-handed amino acids or right-handed DNA with right-handed amino acids. So therefore, these structures are more stable in the sense of Gibbs free energy. So it's more likely that left-handed amino acids is going to be attracted, have greater affinity to right-handed DNA than it would to a left-handed DNA. Now, it could have been the other way around. Today, we have right-handed DNA and left-handed amino acids, but it could have been that we have left-handed DNA and right-handed amino acids. So it depends on what hemisphere life started, but only on the hemisphere and nothing else. Okay, so this is the case. We have right-handed DNA and left-handed amino acids. And we also have another effect that we have an increase here of about 4 times. We don't see it here on the graph, but I have this times 4, just because if we plotted it on a graph, we wouldn't see these dips in the other curves. So we just put a factor of times 4. So all these values for DNA with tryptophan should be multiplied by 4. So they're much, much stronger. This is the dichroism spectrum, or that is how the different right and left-handed DNAs absorb right-handed circularly polarized light. This 0.07% that we mentioned in the previous slide. Now this is 0.07%. Okay, so then in conclusions, well, we are assuming that light's function. This is basically the whole theory of the thermodynamic dissipation theory of the origin of life. Life's basic function, or most fundamental function, is to turn sunlight into heat, and that is dissipation. And that is in fact what all irreversible processes are doing. Not only life, but also hurricanes and convection cells and the Belousov-Zhabotinsky. That's all what they're doing, is turning a generalized force over the system into to dissipate into, for example, if it's sunlight, into heat. But if it's in terms of chemical potential, into products, different chemical products, which is dissipation, just a different type of force of the system. And well, we mentioned that all of the fundamental molecules, or most of them at least, were probably dissipatively structured, just as a hurricane is dissipatively structured. And they all seem to fit very nicely along the curve of the sunlight, which was arriving at Earth's surface in the UVC at that time. And we gave also an explanation of the replication without enzymes of DNA and RNA at the origin of life based on photon dissipation. And today we have talked about how homochirality comes about, given the fact that they are chiral molecules, and the right-handed DNA absorbs differently than left-handed DNA. If we have right-handed circular polarized light in the afternoon, it absorbs a little bit more, so that gives rise to a little bit more of denaturing. And because the effect is temperature dependent, and in the afternoon the temperature is greater, we get a much greater denaturing of right-handed DNA compared to left-handed DNA. And so over time, we have come to this homochirality in which all of the molecules have the same chirality. Okay, that's all I wanted to say. So now we have time for questions or comments. Anything which is not understandable, let me know, and I'll try to explain it in a different way, and in Spanish if you prefer.
Entonces, ¿los aminoácidos solamente tienen esa homoquiralidad porque así se acoplan mejor al ADN y no por otra cosa?
Well, for two things. First, that they have a larger affinity. ¿Sí, Esmeralda? ¿O quiere que hablo en español? ¿O está bien en inglés?
Creo que está bien en inglés.
Okay, first because they have a greater affinity, no? And so they are more stable, so they're gonna stick together much more than if we had, for example, left-handed DNA and left-handed amino acids. We have less affinity, less attraction, so they would fall off more easily. And also because when we have right-handed DNA and left-handed amino acids, for example, in the case of tryptophan, which also absorbs light in this region, then we get a much greater difference in this circular dichroism spectrum, meaning that the combination of the amino acid and the DNA, if they're opposite chirality, causes a greater difference in the absorption of right-handed ultraviolet light in the 260 nanometer region. Okay, so there's like two combined effects. The attraction, but also the fact that we have a greater, for example, if we had this situation of, or let's say this situation of right-handed DNA with right-handed amino acids, then we would find that this curve is not so deep, flattens out. Okay, so the two components, one is the affinity, and the other one is the circular dichroism, which increases because of the different chiralities of the two. So that's rather interesting that this is happening.
¿Y existen los aminoácidos con homoquilaridad izquierda? ¿O no existen?
Yes, you can produce them, in fact, in the meteorites. Because, as I mentioned, the energy is practically degenerate except for the small weak component, but we can even neglect it because it is so small. And we should expect from probabilities, given Boltzmann's probabilities for the Gibbs free energies, based on the Gibbs free energies, we should expect equal probabilities of both of them. And in fact, we do find that in the meteorites. We do find some meteorites which have a little bit more right-handed DNA or right-handed nucleobases with their sugar and the phosphate group. Well, we don't even actually find that. We find not DNA, but amino acids. Okay, I think they have found the bases, but not bases with sugars or with phosphate in meteorites, but they have found the amino acids. And when they look at the concentrations, they find practically equal ratios. So there's experimental error, no? And there are also possibilities that they were formed in a region of space which was subjected to this circular polarized light, which caused a difference in the photolysis of one compared to the other. But basically, they're the same probabilities or concentrations of the different amino acids. So yes, they found left-handed amino acids in meteorites about the same proportion as right-handed amino acids. And there are other amino acids, for example, which life does not use. I think they found something like 60 different amino acids, but life is only using about 22. And in all cases, they found relatively equal concentrations of the different chiralities.
Y si existen, bueno, si en los meteoritos hay left-handed, no es cierto, right-handed amino acids, tal vez también se pueda encontrar left-handed ADN, porque, bueno, si existen en iguales proporciones.
Okay, but to define left-handed DNA, then we have to look at this picture, which, this picture here, which, okay, so this is the base of DNA, adenine, guanine, cytosine, thymine. And this is the sugar, and this is the phosphate group. So really, here to define the chirality, we need to find the base and the sugar and the phosphate group, because it's different for right and left. But it's this big molecule. And as far as I know, they have not found these complete molecules. They have found the bases, some of the bases, like adenine, which is the easiest one to produce. But they have not found the base with the sugar and with the phosphate group also. So in that case, it would be impossible to define a chirality only on the basis of the base. They would have to try to find these, which they haven't, as far as I'm aware, so far.
Y entonces, ¿con qué se como aliarían los aminoácidos con quiralidad derecha? Si a los aminoácidos con quiralidad izquierda se llevan como mejor con el ADN con quiralidad derecha, entonces no tiene sentido.
No, but in space, the probabilities of right and left amino are the same. They're not different. Only on Earth, through organic chemistry with living systems, do they become different. So on Earth, they are different. Those which were produced on Earth by living systems, we would have basically left-handed DNA. left-handed amino acids and right-handed DNA. But in space, where they're produced by these non-organic methods, they're produced practically equally. But that may not have been the case at the origin of life. If life started on the ocean surface, well, we did have this difference, important difference in the circular polarization of light in the afternoon and in the morning, based on this UV tar mechanism of replication or denaturing and then replication. Okay, Esmeralda, I'm not sure if I answered you well. Yes? Okay. Anyone else? Leo or Ivan? Leo, you have to look at the other two videos, I guess, to get a proper idea of what we're talking about today.
Sí, justo.
Okay. It's not that complicated. I try to talk very slow so that you understand me. And if you don't understand it, then ask me. Next class, we can review this. Okay, Ivan?
No.
Okay, well, you've seen some of this before, so I imagine that you don't have many questions left anymore. Okay, well, that's all I wanted to talk about today. So if you haven't done your homework, please do your homework, Esmeralda, Leo. Okay, and inform the others to do their homework. Andres is getting a little bit worried that, not Andres, Roberto is getting a little worried that it's not receiving homework from you guys. Some of them have, but not all of you. Okay, we have 4 homeworks now. We'll probably give like 2 or 3 more before we finish the course. Okay, well, if not, then I'm going to, well, first leave this and say goodbye and finish the
Carol,